Welcome back, everyone. We have our next guest ready already. Hey, Justin. How are you
Hi.
doing?
Doing well. Thank you for accommodating the West Coast time zone out here.
Yeah, well, I'm quite used to it now. I've become quite friendly with Seattle over the last 2 years. Which is also like when we saw each other last time, we had the Hex up in Seattle, right? I think that was last October. It must have been.
That's
So
right.
like a year ago,
Yeah.
actually. Yeah. Almost a year,
Yeah.
more, a little more than a year ago. So let me just look at who you actually are. I mean, no, I know you work at Salesforce. Yeah, are you still at Salesforce?
Yes, that's correct.
All right, and you wrote the Lua target, which made quite a splash a couple of years ago. That must have been, oh, that was a Paris event, 2016, something like that.
Yeah, it was around there. It was kind of rough at the beginning, and I feel like it's only recently achieved a level of maturity for to use in projects that people are
Yeah.
building off of.
Yeah, remember you were saying that was sort of like your we have a baby in the house now project, right? Where it's like if I can't sleep anyway, I may as well.
That's
All
right.
right.
Yeah,
Yeah.
I got some time off from work, and I was prepared to add some extra help for my son, who was just born. But then all of our family swooped in, and as the as the dad, you kind of the grandparents come in and they're like, "Don't worry, we got this," and they you basically just sit on a couch for most of the day, and so that was when I decided to start making a hacks target.
So, see, there you go. Um, all right, so then we'll tune you over for your talk and see you after.
Sounds great.
Go for it.
All right. So I'm Justin, and today we're going to talk about parsing expression grammars in Haxe. And I wanted to give a little bit of a background of uh, just a little bit more about me. As was already mentioned, I wrote the Lua target. I've been using Haxe for a long time. It's over 10 years now, at least. So it's been I had I used it previously in some of the work I did on visualization, and um, and I've always really loved the language and how well thought out everything was, and so contributing that Lua target was mainly just an excuse to do to do more with hacks. My regular background is actually in machine learning, and that's what I focus on mainly at Salesforce. And I haven't quite figured out a way to do an intersection with hacks and machine learning, but I'm trying to advocate for some language features that I think will help hacks in the future kind of adapt to some of these data processing machine learning pipelines. More on that later. But also, as mentioned, I'm out here in Seattle, and it's been great. Like just being mentioned about a year ago, and in the years prior, FlowPlay sponsored some of the hacks meetups and some of the mini conferences we had, and so they were in my backyard. So for all these years, hacks the hacks was focused in Western Europe, and now I had it in my backyard, so that was great. We started hosting some mini meetups. This is a picture of one of them, and of course, this was all in the time before COVID. So right as these were kind of getting started, now everything shut down, and we're back to virtual meetings, etc. So I'm hopeful we can get these kicked off again. There's loads of great places out here to grab a beer, and I'm positive that once things return to some semblance of normal, we'll kick those off again, and I'll look forward to seeing everybody again for that. So I wanted to cover kind of the quick, who, what, when, where, and why of this talk, and these are the things I'm going to cover today. And a lot of it is, if you're not familiar with parsing expression grammars, I'll just give a quick overview of what they are and why I think they're important, especially for just the different use cases that Haxe runs into, and then some of the quirks and particulars about the runtimes and the targets it supports. I want to talk about some of the investigation I did into different alternatives, and some of them that exist already, such as Regex. I want to talk about some of the early experiments I've done for adapting parsing expression grammars and getting it working in Haxe and what the opportunities are there, and then talk about kind of a timeline for when I think people will be able to practically use these. So going even further back, I want to talk about why I got interested in parsing at all. And really this all stemmed from problems with the Lua target. Lua, as some of you may know, it lags behind some of the other targets in different types of performance benchmarks that we started making. And in some cases, it performs so poorly that the benchmark doesn't even finish for Lua. And so Simon put this list together, and I was aware that Lua was slow. I didn't realize it was this slow. And some of the problems stem from Lua being very, I guess you could call it, Lua is the antithesis of batteries included. There's very, very few data structures or routines that are baked in to Lua. And so I had to write most of the implementation there from scratch and rely on pure Haxe solutions. So the JSON parser, for instance, is a pure Haxe solution. And most of the languages use FFI wrappers around native code. So it's not really running Haxe code, it's just calling into some faster C code. And Lua doesn't have that yet. And so one thought I had was I'll just wrap I'll just do the same thing. I'll wrap some fast C code or some other libraries and go about it that way. And I'm going to play this video and mute it. This will go on too long. But there's this concept in programming, and I don't know if this is an American thing, but we call it yak shaving. So this guy's trying to fix a light bulb. And this montage is just him showing him all the different things he's finding that are broken and all the steps he's doing to try and fix the original light bulb. And now he's gotten distracted. Now he's trying to fix a drawer. And now he needs some WD-40 as a lubricant, but he's out of that. So it's this long process, and this happens in, I think this is a good kind of comparison between open source and professional work. Professional work, you just solve the problem you were given. So in this case, make the JSON parsing faster. But since this is open source, you're taking a deeper look at the problem and saying what's, we could just fix this, it'd be so much better. And so it's really common to go on these long journeys to try to get at the deeper root of a problem. And so that was what kind of got me down the path of what can we do to speed up parsing? So I hit on right away, there's some recent, if you just sort of look at the recent advancements in parsing, you'll come across pegs. And so as an introduction to this, you'll see, some of the early work from Brian Ford in 2004. Now that's somewhat of a long time ago. However, most parsers, including Regex and a lot of the concepts behind it, come from the 70s. So it's really kind of an ancient theory that is behind most of the parsers that are common. So pegs are somewhat newer, and they have a lot of great features. And so I'm kind of highlighting some of the concepts here. It's a context-free grammar for formally specifying syntax, and then there's a special layer on top of pegs called pack-rat parsing that operate in guaranteed linear time through the use of memoization. So the trade-off here is that, or the benefits here are that this type of parsing is guaranteed linear, which is very easy. Is also there's a lot of opportunity there for optimization and speed. And the use of memoization, the trade-off there is obviously with memory. But memory's cheap these days. It's not the 1970s. We can throw more memory at a parsing problem. So this seemed like a good trade-off to make, and it seemed like a good application of modern theory. So I want to talk about where parsing and expression grammars fit. If you have a little bit of a formal computer science background, you might be familiar with the notion of LL parsing and LR parsing, and more or less these are broad categories of how to break apart a sequence of tokens or what have you into some sort of organized structure. And so you have two main approaches. One is everything is left to right, more or less, in parsing theory. But the idea is here: do you focus on solving for the first token first or the last token first? And so LL basically is a leftmost derivation. So you're starting with you're focusing on the left most token first. And because of that, because we normally write, most languages are written left to right. It's a little bit easier to conceive of the parsing format for that in your head, and it's easier to write by hand. It also supports incremental parsing, and by virtue of both those, it also tends to be faster. And so PEG is basically in this camp, and also another popular one called Antler. The other option is LR parsing, and you'll see sometimes different parsers and compilers will use this, and they can wind up being a lot more flexible and powerful, but they also require that the entire parsing sequence be solved first before you can start analyzing it. So they tend to be a little bit slower, but you get a trade-off of complexity where you can do different things. So PEG is in the LL camp, and so kind of building off that and understanding which family it's in. There's you'll commonly see parsers with parentheses where you say it's an LL1. That means you've got one token look ahead. LLK, you've got K tokens look ahead, and then you've got LL star, which is a fancy way of saying it's the technical term is a nomenclative outlier parser type, and these basically have this. This is capturing this concept of syntactic and semantic predicates. And this is also going to intersect with that notion of memoization. We're basically capturing parts of the parse that we want to reuse. And so it's a fancy way of just saying we're going to stash some stuff in memory beyond the tokens that we're reading in. And so the specification of PEG is actually, I think, extremely simple. This is kind of a wordy slide, but there's basically two rules that you can see here, and you've got an atomic parsing expression, and then a way of combining those atomic parsing expressions with sequence or ordered choice, etc. And so this is a very simple set of rules, and just for comparison, think of like what you'd have to do to describe regex, for instance. This is way simpler. It fits on, one screen, and that's a big plus. And I wanted to talk a little bit about those, but I want to talk a little bit about those syntactic and semantic predicates, because that's where things get a little different. So to really kind of express those or show how those get used, you can look at a what's called a PEG grammar. The grammar is where you express or encode those different expressions and combine them in a single grammar. So here's a grammar. This is just showing basic math operations. So you've got just noting the final parse state, which is a valid expression. There's a simple sequence notation, so you can see how the expression is a sum, and then there's a sum, which is it could be a sequence of different plus or minus operations with a product, et cetera, et cetera. And then there's some other. PEG also reuses some concepts from regex, so you can see how there's a range syntax. There's different associativity rules, so you can see how power actually refers to itself. And then, but there's some gotchas here as well, and there's some limitations. For instance, in this expression, I intentionally added a expression that causes infinite recursions in pegs. And so this is one of these things where it's completely valid within the grammar, but we won't ever finish if you actually try to run this. So one question is just scan this real quickly and see if you can spot it. And then also think about like there's some other things that seem to be similar to regex. You've got the star, or it's called a clean star. You've also got the question mark notation. Those seem similar to regex, but there's some important differences there as well. So let's look at like some of those. Let's compare and contrast with regex. So the problematic expression that causes recursion is in red there. Pardon. We can't have left recursive associativity in the PEG, mainly because PEG is running in linear linear time, so it's got to basically be guaranteed to resolve. And so if you have a leftmost expression referring to itself, it will never resolve. It will keep trying to expand that. So that's a no-no in PEG, whereas other parsers, that's permitted. Some of the semantics here are identical to regex, such as range support, and then others are kind of different in subtle ways. So one of them is the star wildcards. These are always greedy. That means they'll always capture as much as possible. So PEG has this tendency or this behavior to always be greedy and always take the first thing that it can find. And it's a constraint. It's a little bit different than regex, but the trade-off and the payoff here is that you're getting a lot of speed without having, and there's ways to overcome or adapt to some of these limitations by using these grammars to express different states within your parse. So once again, like comparing this to regex, it supports grammars of non-terminal symbols. It supports only greedy wildcards, supports only forward matches, no backtracking. And then it's similar to other approaches like context-free grammars. So in fact, when I saw this, I said, "Oh, isn't this just a context-free grammar?" But it has some constraints on top of context-free grammars as well, because it's only going to support non-ambiguous choices. So one example of that is called the dangling else ambiguity, where you've got if then, if A, then if B, then S, else S2. In a context-free grammar, you can basically there's two valid states that you could build from that. But PEG doesn't permit that. You have to. It basically always defaults to the first one it can solve through what's called implicit prioritization. So basically, all this is just saying it's emphasizing speed, certainty, and then it's giving you some mechanisms for expressiveness through these different expressions that you can create in the grammar. So yeah, restating that as well, focus on speed and ease of writing. It uses some regex constructs. You have to adapt your understanding of those a little bit so that you know the way that PEG is handling wildcards, etc. I'll skip through some of these using memoization. And jumping down to the punchline here, PEG parsing maintains the speed of LLK parsing, but may use more memory, which we already mentioned that's okay. Like most computers now have plenty of memory, and so this is a good trade-off, I think. And a lot of other people have have hit on this well before me, and have written series of blog posts saying like, "Hey, this is good. This is better than regex. We should be using this." And so there's some links here I've added to different blog series from Guido and Roberto, and these are both the authors of Python and Lua, and they're trying to kind of steer the boat and say, hey, speaking to their community, saying, hey guys, we should be doing, this is a much better way of handling parsing. So I'm going to make the same argument. As an example of like, what does a practical grammar look like? Here is the specification for JSON, which looks a little bit complicated, but at the same time, once again, this fits on a single screen. And then once you learn how to parse or how to mentally read these expressions, you very quickly understand how they're building up a grammar, basically how to parse in this case, a JSON string. And you realize that like this is very terse, and this is actually pleasant to read compared to if you actually look through the source codes for various JSON parsers. It's full of for loops and all kinds of different like string splitting things, and you really have to track it. It's nice. It's nicely composed. Like you can clearly understand each individual expression, and then you can understand how higher order expressions combine them in different ways. So once again, I'm going to continue to harp on regular expressions because these have a long history. They're very common across different languages, but they're problematic in a lot of ways. So this is Jamie Zielinski. He's a famous programmer. He wrote. Well, you'll have to Google about all the things he's done, but he was basically responsible for some of the early browser implementations and kind of launched a lot of the focus on getting normal people onto the web. So this is one of his famous regex sayings, and I run into this a lot. So I try using regular expressions in my own projects, and they solve some problems, but they also cause a lot of problems, and they're very difficult to deal with in terms of debugging them. So the why or the why not of regex is that regex is available. It's part of the standard distribution for Haxe. Like you can find an implementation in every language that Haxe supports, but they always feel a little bit awkward. Like they're not composable, so you can't really combine regexes, mainly because of the backtracing component. The syntax is in string form, and I know there's some fancy ways you can have a version of the syntax parsing that's only specific to regexes, and some editors support that, some don't. But it's very awkward to kind of visualize what's happening with the regex. It's also really difficult to extract structured group matches. Everything has to be in one regex more or less, and then you have to capture things with index-based subgroup matching, which it's difficult to keep track of like which group refers to which index, and especially if you're capturing optional groups, etc. That's just a pain. And then there's some snags and caveats surrounding matching with Unicode and UTF-8, but I don't want to go into that. It's basically just there's certain flags and special characters in regex that on some set platforms behave differently, and you just need to avoid them or be aware of them. So all that is a lot of mental overhead. And then on the right here, this is one of my favorite Stack Overflow comments. And it might be a little bit small to read, but it's answering the question of like, how do you parse HTML with regex? And this is just everyone if you're a programmer for long enough, you realize it's just, it seems simple, but then at the end, like it will just drive you mad. So this is upvoted 4,000 times, and someone's trying to explain why you can't use regex to parse HTML, and it devolves into the commenter here going completely crazy by the end of the comment. So it was a little bit of a joke, but it's basically regex has severe limitations. It gets you down the road a little bit, but it's going to drive you mad. That's the punchline. So now let me talk about like what does it take to get Peg and Haxe sort of as a first class citizen. And keeping in mind, I wanted to originally investigate Peg for JSON parsing, and that native Peg implementations seem to exist for most languages and runtimes. Peg notation, if you remember back to that JSON grammar, it uses common math operators. So like you've got, they just pop up in the grammar. And as you know, Haxe supports abstract types, which can have overloaded math operators. So once again, this is something where maybe you have a grammar of abstract operators where you can capture these individual expressions and build them, just with variables, which would be great. And then Peg can handle deserialization tasks primarily. And one thing you run into is that Haxe has kind of a special array and object data structure. And it's based kind of off ECMAScript, so JavaScript and ActionScript kind of follow it closely, but some of these other languages, especially Lua, don't really follow that at all. And so if you want to deserialize into Haxe structures such as basic arrays, you've got to have some low-level support for that. And relying on a third-party library for that or whatever is going to cause problems. Case in point, once again, Lua tables, for instance, are one-based index, and whereas Haxe arrays, of course, are a zero-based index. So you can't, right off the bat, you can't rely on a Lua library for decoding JSON, because it will do it in a different way. And at the same time, it's impractical to write or wrap speedy raw parsers. Like nobody wants to go and adapt a bunch of C code for every serialization format that comes out. So it's going to be, especially for Lua, it's a painful and persistent problem. So I'll cut to the chase. Here's my stab at Peg and Haxe, and this is for the Lua target. And I'm right now I have this committed in the main Haxe repo on a branch called Lua LPeg, and you can kind of see some examples of in the syntax here. This R is a range operator. This CC here is a constant, and what I'm doing is I'm using variables and then and abstracts under the hood here to compose a grammar, which is more or less what I wanted to do. So I was really pleased to get to this part. And as an example of what you can do here, I'm matching this. I'm using this peg to match against this string. But one of the fun things is that since you've got each individual expression as a grammar, you can do different things. Like, for instance, this range. I'm matching against that range, but then I'm also applying a Haxe's standard parse float against that. So I can convert that to a number. And then there's other, I'm using a capture function here where I'm capturing all list matches together and adding them together. So basically what this is doing is it's not only matching this, but it's also converting it and then doing some other, I'm also composing like what to do with the parse as well. So you get this combination of how to parse out the data structure and then immediately apply something to it, like some other lower level parsing function. And the whole thing just you can compose these things relatively quickly, and it's way more pleasant and functional than kind of dealing with the heavyweight regex or basic string splitting techniques. So anyways, this is working pretty well. And however, there's some, I immediately ran into some snags. Here's just some of the positives on the top here. I'm not doing anything specific to Lua here. This is using a Lua peg library, but it's doing all the first class features that I wanted, and that I believe can be easily added to virtually any other target runtime. However, the negatives are it's a bit wonky because Lua LPeg's runtime is once again a little opinionated, and it's in one aspect of that is it's a little bit too dynamic, and I don't want to go into that, but I didn't feel comfortable building a generic peg implementation based off of Lua's notion of how peg parsing should happen. So I kind of want to take a step back at this point and use like a raw peg library for this. So I made some progress here, but I think it needs I think I might come at this in a slightly different way for kind of a good first class Haxe implementation. So and the reasons are, once again, Lua's library kind of endorses or encourages even some patterns that aren't type safe. And once again, I can go into more details offline on that. And then using Haxe's abstract types for operators, I think is kind of a no-brainer. But I realize it's not really a complete match to peg grammars. And there's more on that as well. But it seems like there's some every implementation I've seen uses a different kind of combination of operators. LPeg, the Lua version, had its own version of operators it was using, and then I think Haxe probably needs a different variation of that as well. So that's another thing I just need to resolve, and this will probably come as a Haxe lib rather than as part of the core Haxe library until I feel like everyone's kind of happy with the operators there. All this in the meantime, like once again going back to the notion of like I was realizing JSON parsing still slow. I'm getting deeper and deeper into this peg parsing hole. So I went back and looked at. I said, well, I at least should be able to solve SIMD. I should at least be able to solve JSON parsing. So I found this JSON parser that's extremely fast called SIMD JSON, and wrap the C++ in Lua and use that just in the meantime here. And the SIMD JSON library is extremely fast, and it's actually faster than the peg parser that I thought was going to be so fast. But the key feature of SIMD JSON is actually using it's using SIMD, so single instruction, multiple data. So it's using more parallelization inside the that most CPUs support. And so I reached out to the author of SIMD JSON. I was like, I think this approach you use for JSON parsing would be great for PEG. Like it seems like it could follow the same patterns. And so on the right here, you'll see a Twitter conversation or part of one I'm having with the authors of SIMD JSON. And I'm trying to get them to do a PEG parser for this and kind of make it more of a general solution. So that's pending. And then I'm also started. I realized I should be working on working with Ammer, who Oral has written, one of the main Haxe contributors, and he has support for Lua in that library, but it has a couple of kinks that we're working out, and so there's a couple different loose threads here that I'm tracking down, but it seems like there's a lot of things coming together at the same time, and I just kicking this off in June. I needed a little more time to polish off some of the edges. So the plan is for the next couple steps here. Like when do I see this like all coming together? I need to fix the extern generator for Lua, which basically at this point is just getting the CI to run consistently, and then find the PEG library I want to use for FFI. I'll use SIMD PEG if and when it's available. The SIMD JSON implementation was amazing, so I'm really hopeful they follow that up with SIMD PEG, and then for the targets that don't have FFI support, it still should be very easy to find other libraries for those. I feel like those, especially like JavaScript, etc. There's PEG implementations there, and you could probably just reuse those, and then put this on HaxeLib, of course. So that's the plan, and that's the result of going down this rabbit hole of parsing, and I wanted to kind of come back to the summary here in terms of like what are all the things that I'm seeing here and advocating for. Is that Haxe and Lua especially, there's some targets there that need fast parsing routines because they're intrinsically limited. They don't have all the library support, or they're different enough that we can't rely on the third-party library externs. We can't always rely on those native libraries because they don't always support the Haxe data types. There's been these recent-ish improvements to LLM parsing techniques. This PEG and PackRat parsing seems to be the best fit. You can find a lot of people writing about this. I just cherry picked the authors of Python and Lua. They give a strong endorsement of it in a series of blog posts. Also, I'm just saying Regex is awful. We need to move on. I don't see that as being. I just think that we can do way better. That was something that comes from the 70s, and computers have moved on since then. And then to take advantage of some of these faster libraries, we need a better. I'm realizing we need a better mechanism for handling FFI support. And once again, this is for Lua, but there's other libraries as well. The benchmark suite has really exposed how poorly some of our targets perform on some basic operations. So I think really to address that, Haxe code can be very fast, but at some point, like there's, you need something lower level for certain operations, and to do that, we need the FFI support for that. And then it's not that PEG is not necessarily the fastest. There's always going to be something that's manually tuned that's even faster, but it's. But I kind of believe that there's, as especially with these SIMD-based libraries, as more of those come online, we'll be able to take advantage of those and get rid of the major differences in speed. So I'm hopeful for SIMD-PEG, and keep your eyes open for for other libraries like this, and talk them up, because we've benefited from this a lot on finding these really robust and stable native libraries. And another one is libuv, for instance, and the whole Haxe ecosystem benefits from that, because then we can use kind of the identical or the stable C libraries for all of the different target behaviors. So that would be a point where we have the best of both worlds, and then we can write really fast parsing routines in pure Haxe using expression grammars. So that's all I got. Here's my Twitter and GitHub handles. If you want to reach out and send me a note, happy to talk about this more. And I see that there's a couple questions here. But I might let if Simon or Josephine wants to hop on and.
Well, you can read them yourself if you want.
Okay, I'll read over here. I see they kind of piled up on me. Okay.
You can help them out. Come on.
I'm not sure, because I think there was only one, which was about really curious how you include native Lua extensions. Sound like the Lua output becomes kind of platform specific because you need a Lua VM extension.
Yeah. The Lua, okay. How do you include native Lua extensions? Sounds like the Lua output becomes kind of platform specific. So you're right. Maybe I can interpret this as, I guess I could just back up and say the way that Haxe does Lua is very specific to Haxe, and that's because it's all organized around with the basic Haxe data structures, such as array, etc. And so Lua uses tables, and you can use tables in Haxe, but they're basically externed and specific to Lua, so they're no longer general. So that's kind of a problem. So you can use Haxe to write pure Lua, but it's just not as ergonomic. And then I think the Lua output does then become platform specific, or rather like Haxe specific. And then, Lua accepts native extensions, and those native extensions need to be managed for each operating system type, et cetera, platform. But luckily, Lua already manages that. There's a Lua Rocks package manager, and Lua is basically you can think of it as like a very thin scripting layer on top of C. So it's basically built. One of the things it expects is a C compiler, and if you can manage that, then it will be happy. If you can compile the native code. And then one of the other questions is, I think one of the constant things we're struggling with is that a lot of people just want to use pure Lua, even though it's slower. There's still some use cases where you need that, and one common one is that Lua is used as an embedded language in a lot of. I know it's used in a lot of game development, scripting for different reasons, and one of the reasons it's popular is that Lua can be very memory safe. So you can script in it, but then not leak or get access to memory that you shouldn't have. So it's very popular for like user or community contributed extensions for that reason. And when you write those extensions, they don't give you any of the other like native library code to use. So you have to only use what we call vanilla Lua. So I've got there's one flag that you can pass into the Haxe compiler that called Lua vanilla. And it will strip out, it'll basically try to use the just pure Lua, pure Haxe implementations of all these libraries. And it's right now I'm kind of stammering a bit because it's a little awkward itself. There's some reasons for that, and I'm trying to think of better ways of handling that. But right now there is at least one mechanism for managing that.
All right. Thank you very much.
Yeah, you bet.
All right. So nice to see you.
Yeah,
Thank you very much for showing up.
Yes.
Yeah.
All right. So we'll be on another quick break. And then also like we're a little bit behind, but that's actually my fault. I thought you were only gonna take half an hour. But that was my fault. So anyway, but it's fine. We've got time.
Right.
All right.
So
So see you in a bit.
see you.